Hello! Today I continue to explore AVR and specifically microcontroller called ATmega328P with the help of Arduino. And this is third episode in which I will discuss how I do the ADC, so analog to digital conversion. And inside this microcontroller we already have this ADC, analog to digital converter. So we will find out how to use it and how we can drive this potentiometer, especially read this potentiometer. And for example, if it will be below some value, I set it to be below 512, and where these values come from I will tell you in a bit. So if it's below 512, that means this built-in LED that we drove in my previous videos will be turned on. So let's try that. Okay, so we will do something like this. Now this is maximum value. I will make it lower. Here we go. Our LED is light, I would say on. And back again to high values. Here we go. And 512 is a value that is in the middle of the 1024, so 1024. This value is something we will use in our ADC. And first of all, I wanted to talk about what ADC is itself. Okay, so what is ADC? ADC is analog to digital converter. And this is a circuit, so essentially like a black box. And this circuit, this black box, will take in some values and output some other values. And as I said, analog values, but in our case, it will be analog voltage. So V analog, and output some digital value. And this value will be in form of zeros and ones. So for example, 0, 1, 1, 1, 1, 0, 0, and so on. We can choose what range of voltage, input voltage will be, and I chose it to be from 0 volts to 5 volts maximum. And we do this by setting some register things, and again, we will talk about this in a bit. So essentially it will be from 0 to 5 volts. We will output some value in binary, but for humans, to read it easier, we will say that it will be from 0 to some maximum value. Maximum value in our case, in ATmega328P, will be 1023. And where does this value come from? This is 10 bits. So if we raise 2 to the power of 10, we will get 1023. 10 bits is a resolution of our ADC. And I think 8 bits AVR chose 8 bits would be too small or imperfect readings, but 10 bits would be okay. You don't need to actually care about this because AVR already did it for us, and it will be stored. We will access it using only one variable. This variable, I should say macro, not variable, but macro. This macro will be called ADC. Now, if we go to the datasheet of ATmega328P, we can scroll down to section 23.9, register description of analog to digital converter. And the very first register that we see here is ADMUX, ADC multiplexer selection register. Essentially, what this register does is just chooses reference of voltage with what voltage it will be compared, or as I say it, with what voltage will be the maximum value. This is probably wrong, but I see it as this. And again, as you can see here, the address of this register inside microcontroller memory is 0x7c. So we can access it by using pointers to this address. But of course, we will not do this, fortunately, and AVR already did this for us. So what we will do is we need to set these registers to some values that we will choose. And let's start from the most significant bits. So these are bit 7 and bit 6, or they called ref S1 or ref S0. This is just naming instead of saying bit number 6, bit number 7. It's a bit confusing. We'll just use ref S1, ref S0. So these first two registers, as we can see here, it is reference selection bits. And this is just voltage reference. We will use configuration of bits. So either 0, 0 or 0, 1. So 0, 1 or 1, 0 and 1, 1. So these all configurations that we can use, but what I will use is this. And this is essentially will set automatically our and this essentially will choose automatically what our system is using, which is 5 volts, if I'm not mistaken. So what we need to do is set AD max bit number 7 and bit number 6 to be 0 and 1 respectively, or just set bit number 6 to 1. Next, bit number 5, I'm not using it, and essentially, to be honest, I don't know what this thing is, what it does, but we are not using this in this example. Bit number 4 is not used, it's blank, and other 4 bits, 0 through 3, they called max 0, max 1, 2, and 3. These are pin selection bits. This just means that we can choose which pin of ATmega328P we will use. We need to choose, but we choose it using a sequence of bits, and this sequence is here. So here we have ADC 0 through, I think, 8, right? Or they say that it's for temperature sensor. I'm not sure if we can use it or we cannot use it, but this is internal temperature. We'll just ignore it. So essentially what we have is 9 pins from ADC 0 pin to 8 pin. And in my case, I chose ADC pin number 5. I don't know why, just because. You can choose any other, but I chose ADC 5. To choose this bit, we need to set AD max to this value, so 0, 1, 0, 1. That means we will set max 3 to 0, max 2 to 1, max 1 to 0, and max 0 to 1. So 0, 1, 0, 1. This will just tell microcontroller, use pin number 5, ADC number 5. And that's what we do here. So this is in the initialization of ADC. Again, we shouldn't use it like that, as I described in my previous videos, because this is kind of unsafe way to do this. But for the learning purposes, for visualization, I think it's better to write it as this. So again, 0, 1 inside AD max is this 0, 1. And this sequence gives us AVCC, external capacitor. So this just means we will not connect anything, and we don't need to do anything. It will use 5 volts in my case. Next, what I do is 0, 0. We just skip these things and leave them. By default, everything is 0. So we'll just leave it as 0, 0. And next thing, 0, 1, 0, 1. This is just tells us to use ADC pin 5 of ATmega328P. Second register, ADC SRA. This register will enable ADC, start ADC conversion, and provide clock for our ADC. Why do we need clock for our ADC? Our ADC is special ADC, which is called successive approximation ADC, something like that. This is whole another topic, and to be honest, I don't understand it like very well, but what I learned is that it just needs clock to step through each step of conversion. So when it does conversion, for example, it will do first command, then after some time it will do second command, then after some time it will do third command. So what we will do is we will divide main clock by whatever we choose value. In this case, it's in binary 111. In decimal, it's 128. So we will divide main clock by 128. And I think this is what datasheet itself tells us to do. So let's see ADC SRA. So this is ADC control and status register. I don't know, just A. Address, if you want to know, this is 7A, 0x7A. And here we have different bits. Bit number 7 is ADEN, which is ADC enable. This will just tell microcontroller to enable or turn on ADC. Next is ADSC, which is ADC start conversion. This will actually start our ADC conversion. So again, we first enable or turn on our ADC, then we can tell it to start by passing 1 inside this bit. These bits, I don't know what they are, and I'm not using it. I'm not using them, so we'll just skip them. And these bits will tell our microcontroller, our ADC, by what value to divide our clock. If we scroll down, here we can see the division factor. So here we say 0, 0, 0. All zeros will be division factor of 2. 0, 0, 0, 1 will be division factor of 2 again. Then we have 0, 1, 0, which is 4, 8, 16, and so on up to 128, which is we actually use. So that means we need to put inside these 3 bits all ones. And so that's what I do here. ADC SRA, so enable, but don't start conversion yet, because this is initialization. We will do it here. So do not start conversion. And last 3 bits, divide main clock by 128. Okay, next thing is DDRB. Of course, we know this. This is just to set port B5 to be output, which is built-in LED on Arduino, and what we used in my example. And then inside the while loop, which will be infinite loop, we tell ADC to start conversion. So as you can see, we put 1 inside bit number 6. Initially, it's 0, but we set it to 6. And again, what this thing means and why this works like that, I already talked in my previous video, so check it out. Next, what we do is we wait for conversion to complete. And this means that ADSC will become 0 when the conversion is done automatically. So we do this. To be honest, I'm not sure how to interpret this thing or how to read this thing. And finally, to read our ADC result, again, as I told you, this ADC result will be inside 2 registers instead of 1 register, because our ADC is 10-bit and it will hold 10-bit value. But of course, it cannot hold 10-bit value because our microcontroller is 8-bit microcontroller. That means we need to use 2 8-bit registers. But AVR, they already done all the heavy lifting for us. So that means we will use variable called value. This variable is unsigned integer of 16 bits. Because again, we use 2 8-bit registers or 1 16-bit. And we assign to this value ADC. This ADC thing is a macro, and it just goes to some register. I think we can actually find it. Yeah, it's actually here, 0x78. So this is the register that holds our ADC value. And yeah, as I said, I'm not sure what the hell is this and this. But okay, we'll just read this value. And this value is ADC 0, 1, 2, blah, 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 and so on. And then we just check this value. Whatever we have value right now, we can actually print this value. But no, I don't think we can, right? Yeah, I'm not sure how to do it. It's not Python. Sorry about that. But if we would print this value, it would show us binary value. Whatever 10-bit binary value we will have right now at this particular moment when we read from input pin or wherever we connected middle leg of potentiometer. So yeah, I think that's it for today's video. This was very challenging for me, and I'm not actually sure about other things. So yeah, it was like very fundamental intro to ADC in AVR for me, probably for you if you enjoyed it, but it works. And maybe in the next video I will try to hook up the actual sensor. Probably we will do temperature sensor, which is very easy sensor to understand. I hope you liked this episode, and I'll see you in the next one.